Okay, good morning, everyone. Welcome to this Wednesday morning session. We are very happy to have here Melanie Graf from the University of Hamburg. She will talk about initial data sets which do not satisfy Regge-Teitelboim conditions.
Yeah, thank you. I'm happy to be here and give a talk. I'm also very happy that I made it here on time, despite the snow, which caused some delays with public transport, but everything worked out fine. So, yes, it's a very lengthy title. This is joint work with Euclidean and Jan Metzger. It's done, but it's not, the mathematics is done, the write-up is still in progress, and it's also not on the archive yet. There's a bit of a more introductory write-up or announcement of results with me and Carla that's on the archive already, so you can find a little bit there if you want to look. That has the more evocative title of Coordinates Are Messy, which is kind of the backstory of this entire thing. So we will see that. Actually, it will turn out it will be not too bad in the end, but one can do weird things with coordinates. Also, initial data sets, I will abbreviate with IDS, and Regge-Teitelboim, I will abbreviate with RT, and I hope to not write these words on the blackboard again during this talk. Okay, yeah, so we will consider examples that do not satisfy the Regge-Teitelboim conditions. First, I need to give you some definitions. Then I should tell you why the Regge-Teitelboim conditions are important, because else no one will care. And then the main point, and this is not in the title because it's already long, but the main point will be we do not satisfy the Regge-Teitelboim conditions in any coordinates. No matter which asymptotically Euclidean coordinates we choose, we can never make them good enough to have the Regge-Teitelboim conditions. Okay, so we are in the setting of asymptotically flat initial data sets. And such an asymptotically flat initial data set is Riemannian manifold MG and a symmetric 0-2 tensor K, which, if the entire thing sits in a space-time, is the second fundamental form, but we can also consider it on its own, as probably all of you know. I will be talking about the three-dimensional case. We are very confident that everything works n-dimensionally, but then I would have to remember all of the decay coefficients with the n. And also, we did not check the n-dimensional thing very carefully yet, but we don't see any reason why it would not work. Three-dimensional with such that there exists a diffeomorphism phi from some asymptotic region, M without C, which is compact, to R3 without some ball. Okay, and I should write tinier because else I will have to clean the blackboard a ton. Diffeomorphism such that in this diffeomorphism psi, in coordinates induced by psi, phi, we want the following conditions, and I should have put compact here. Gij, so the components of the push forward of the metric minus delta ij should be r to the minus 1/2 minus epsilon, and all of this is for some positive epsilon, and actually we also want the epsilon to be less equal than 1, because once it's larger, we have too nice decay. And Kij would be O1 R minus 3/2 minus epsilon. And then for mu and j, which I should put somewhere what they are, since maybe not everyone remembers, though probably, I mean, I'm very certain that all of you do. This should be just O0 R minus 3 minus epsilon. So let's put mu and k somewhere. Where do I have my mu and k? Mu is 1/2 scalar curvature of the metric plus k squared minus base k squared. Now I need to check. No, minus and plus I have here. So that seems weird, shouldn't it be? Plus. Anyway. Mu would be the divergence. Yes, of course, because you bring it to the other side and then you get mu greater equals 0 implies scalar curvature greater equals 0. Science. Correct, this is a minus. Yeah, my case look a little funny. Okay, and I should maybe say a little bit about the indices here, since maybe not everyone is used to it. The indices indicate up to which order of derivatives we also want the appropriate decay. So O2 would be, so the functions decay like r minus 1/2 minus epsilon, and then the first derivatives also in these coordinates must decay like r minus 3/2 minus epsilon, and the second derivatives must decay like r minus 5/2 minus epsilon. Two indices. Yes, and also for this asymptotically flat definition, one can ask, so how much of this definition is geometric and how much of it is just a condition on the coordinates? And pretty clearly, this is not just a question of the coordinates, but also a question of geometry. I mean, for one, we are fixing the geometry, the topology at infinity. And also, if we look here, then, for example, if k is 0, then this mu just becomes the scalar curvature. So we have a scalar curvature condition, which, for example, implies that the scalar curvature is integrable over M, which is then a purely geometric thing. So I'm not sure how much of that I will write down. So being asymptotically flat is geometric, but perhaps not purely geometric. So geometric because it implies integrability. Of mu or r if k is equal to 0, which clearly gives you some geometric abstraction to admitting such asymptotically Euclidean coordinates, but sorry, missing a knot. Not purely geometric in the sense that even if I have the nicest initial data set I can think of, I can always pick bad coordinates that destroy these. Also not surprising. I do like examples, and that's why I want to mention them. Take new coordinates, y being x times 1 plus a over square root of the radius on R3 with the Euclidean metric and k equals to 0, then an easy computation shows that this satisfies decay for epsilon equal to 0, but not better. And of course, one could do way worse things to these coordinates. I like this example. This goes back to Denisov and Soloviev. because for this example, so one thing that our asymptotically flat condition guarantee us is that the ADM mass is well defined and coordinate independent. And of course, in this example, one can then compute the ADM mass in the y coordinates, and then one gets ADM in the y coordinates, which is something proportional to A. I have it in my notes, a squared over 8, which is not 0, which is of course not what it should be. And it also shows that these conditions with the positive epsilon are really optimal for ADM mass. Yeah. Put it in here. So what do they give us? They guarantee an ADM 1 over 16 pi. Sorry, I should put the energy since we have a non-zero k potentially. Limit r going to infinity. Then we integrate over spheres of this large radius. Then we have some Dij and the j derivative minus the, yeah. Okay, I mean the Dij. I guess, and then we have I R mu as R. So we have the limit of these sphere integrals. Yeah. Yeah, I have my indices switched a bit from what one usually. Not that it. This is probably the way that more recognizable. Okay. Guarantee that this is finite. And coordinate independent in the sense if I choose any other asymptotically flat coordinates, I get the same limit. But as we saw, if we break asymptotic flatness, that's no longer the case. And the counter, so another of these sort of flux integrals at infinity that is related to some physical quantities would be the integral for the center of mass. As it turns out, for the center of mass, one needs additional decay assumptions, and those are exactly the Regge-Teitelboim conditions. Let's see how, okay, I can barely get it back. And the initial data set okay, satisfies the theta Regge-Teitelboim conditions if we have the following Gij, and now so sorry. As I've already alluded to, but not really mentioned fully, if we have too much decay, then the ADM energy will vanish. So we can't just add decay to Gij because then we get 0. So what one does is, with this Regge-Teitelboim condition, is one imposes asymptotic parity conditions, being Gij odd, O2 R minus 1/2 minus epsilon minus eta, where I should put for any f, we have the odd part of x as 1/2 f of x minus f of minus x. And the even part, well, I don't really need to write this down, but I'm already quick. Okay, so what we're doing is we're taking the components of the metric in this chart, and then we compute the even and odd parts in the coordinate x. And if that does not sound very geometric to you, it does not sound super geometric to me either. Or 1. And for k, we need the even ones, r minus 3/2 minus epsilon minus eta. And mu and j, we have odd parts again, 0, r minus 3 minus epsilon minus eta. And we are mainly interested in eta being 1/2 or eta being equals to 1. So for eta equals to 1, we get that the Regge-Teitelboim center of mass, which is, and now I really need my cheat sheet. So is a vector with L components, or 3 components, 1 over 16 pi, the ADM energy. Yeah, and we can already see we do not want the ADM energy to be 0 to define a center of mass, just like in any physical setting where we want to find a center of mass. If the total mass is 0, then this is an ill-defined, ill-posed question. Limit are going to infinity, and then we again have our sphere integrals. The first part is the same thing as in the ADM energy, just multiplied with XL times ADM. And then we get an additional term minus also an integral over SR PIL XI over R minus BII L over R mu sum over all i's. Okay, so eta equals to 1 implies that this is finite. And also independent of the Regge-Teitelboim coordinates that we choose. Yeah. And for eta equals, so also if one looks at this, just like with the ADM mass, one would like to sort of better understand these flux integrals geometrically and what one gets for this limit. So there have been various alternative definitions of the center of mass been proposed that are more or less geometric. So for example, by Huisken and Yao have a CMC center of mass, then Regge-Teitelboim and Anasakovic have an ST-CMC center of mass, which takes into account the K, because if we look here, this is completely devoid of anything involving K, which also is a bit strange, perhaps. And yeah, I think then there's a reformulation by Lan Huang, who rewrites it as some Ricci and scalar curvature terms integrated against conformal killing vector fields. And I think, so certainly for n equals to 1/2, one has equivalences between the Beigo-Merho Regge-Teitelboim center of mass and the Huisken and Yao center of mass. And I think also, I mean, yeah, for the K, including center of mass, one gets a correction term that also works out nicely. So eta equals 1/2 gives you some equivalent. Is to understand geometrically. With the caveat that none of these equivalent expressions need to converge. But if they do converge, they converge to the same thing, and one converges if the other converges. But this is just for a bit of introduction why we why we care about these conditions. And again, just as with the asymptotically flat things, we can ask the question whether these are geometric conditions. And I mean, this is still open, but also whether, so how much geometry is hidden in these conditions, and could it perhaps be that these are still pure coordinate conditions? So could it be that for any asymptotically flat initial data set, we can find some coordinates that do satisfy these Regge-Teitelboim conditions? So I think people coming from a more physics perspective, this would be the question of whether these are pure gauge conditions or whether they actually come from your initial data set itself. And I should also mention at this point, so I do not forget, there have been examples out there by Choquet-Bruhat and Chris Nertz, and also by Lan Huang, who showed, the examples of Choquet-Bruhat and Chris Nertz we will still encounter in our talk, so I'm not going to talk much about it. But if I understood that paper correctly, Lan Huang showed that one can construct solutions to the constraint equations that have very specific decay behavior that violates these Regge-Teitelboim conditions. And then also you get some divergent terms in the center of mass, which but then you get divergent terms here is not the most surprising. But as far as I understood, this was also only in these specific coordinates. So so there has been plenty of stuff done that in specific coordinates, it's relatively okay to find some that do not satisfy these. And one can additionally wish for nice properties. Okay. Yes. And usually I first tell you how we got there or why our examples will be examples, but I decided this time to start with the examples because usually I don't really get to the examples and then I'm rushed. So we do the examples first and then I will tell you why they are examples. So what we are looking at is we're looking at graphs in Schwarzschild. And our Schwarzschild manifold would be, of course, R cross R3 without a ball of radius 2m over 0. I really can't remember things. And our Schwarzschild metric, we can, of course, write with our Labs function n minus n squared dt squared plus n squared dr squared plus our metric on S2 r squared. With n being the square root of 1 minus 2m over r. And we have graph functions from, well, we can, of course, extend the entire thing in some arbitrary way into the interior because we don't really care what happens in the compact set anyways, but we are only going to write them down from 0 to r. And then we can, maybe I should draw something. I can draw over here a little bit. So we have time, and then we have some t. Then, of course, as long as the graph of t is space-like, we get an induced Riemannian metric on here in the second fundamental form, and we get our initial data set. Pt and KT with yes on the graph. We are going to T. Okay, so we have our initial data sets. The nice thing is these initial data sets are vacuum because they lie in Schwarzschild. So we have mu k equal to 0. So we don't need to worry about those guys, which is helpful. And then, of course, since we understand the asymptotics of the Schwarzschild metric very well, we can easily compute the asymptotics of the GT metric and the asymptotics of the second fundamental form. And what we get is, yeah, okay, I should maybe push this up even further. I can. It's this thing. Okay. So we get EIJP. So in the canonical induced coordinates from the Euclidean coordinates on the Riemannian slice of Schwarzschild. It will be Hij minus n squared EIT dJt. And of course, the decay of this is roughly like DIT times dJt. And for the second fundamental form, I'm not going to write down the full formula because that is ugly, but it also exists and can be found or calculated. But essentially what we get for the decay rates we will considering is that this decays like the second derivatives of t plus some lower order terms or higher order depending on your definition of what's lower and what's higher. Okay. And now we can already see that if we prescribe the decay behavior of t, we can sort of very nicely prescribe decay behavior here. And it's also already kind of visible that the G components will decay better than, or usually in these asymptotic conditions, we always want the K components to decay one order better than the metric. But here the decay of the metric is comparatively good to the decay of K, which will help us out. Okay, and concretely, we look at a two-parameter family of T's, T beta gamma with T beta gamma even, let's write E. So we can prescribe decay for the even and odd part separately, and the even part will be either a sine of ln r if beta is equal to 0, or just r to the beta if beta is not equal to 0. So the sine ln r is just to get something that behaves asymptotically constant, but where the derivatives do not vanish, because as soon as the derivatives vanish, we lose anything that we want to get for the decay of GT or KT. Odd being actually this is just u times x over r gamma, sorry, over r times r gamma for any gamma. So again, this is to make it odd and fix the decay rate at gamma. And then we can see what happens for various of these beta and gammas and see whether things satisfy our Regge-Teitelboim conditions or not. let me see how I best for this graph. Okay, we have gamma, we have beta. So first off, we want ideally both of them to be less than 1/2 to make sure that the things are asymptotically Euclidean in these canonical coordinates. And then as it turns out, and we can already kind of, we see this here for the k, the even part of k only sees the even part of t. So we would expect that if the even part of t decays better, then we have some Regge-Teitelboim conditions. If it doesn't, then we do not. And again, this is for these specific coordinates. I will tell you why we can't find any better coordinates after dealing with these specific coordinates. So for theta being positive, we have no Regge-Teitelboim conditions. For beta being until -1/2, we have, yes, and I should cut off. Yeah. Cut off a thing. We have the eta equals 1/2 Regge-Teitelboim conditions, and then from here onwards we have eta equals 1 Teitelboim conditions. The lines themselves are always included in the worst decay and not in the better decay because we need the additional epsilon. Those things. Okay, this is one thing. So this is nice, but then what I figured is, the thing is, in all of these examples, really it's the k that we are worrying about. So this is all because of bad decay. Of k. Another question is, could we? Yeah. Another question would be, could we find if we just, and this is, so the upside of these initial data sets are they're very physically pleasing because they sit in Schwarzschild and have mu equals j equals 0, and we know exactly which spacetime they belong to. However, how to best incorporate the k into the center of mass is, yeah. So there's much less study of the center of mass if one also wants to involve k, then that has already been done for this Riemannian formulation. So from that point of view, it would be nice to have purely Riemannian initial data sets where one also gets similar behavior. It turns out we can do a similar thing here. Let me see if I can get a color. Maybe blue. So we can try blue. We also get I would like to fit it here because then I can leave it on. We also get a Riemannian initial data set. If we just take MT, GT, and then we just, instead of the K we get from Schwarzschild, we just use 0. And then the price we pay is, here we have mu equals to 0. Our Riemannian thing will not have scalar curvature equal to 0, but it will have scalar curvature coming from the K. So once we do this, then these examples see the bad behavior of K on the level of scalar curvature. So not equals 0, but yeah, roughly it works like a k squared. And if we look at k squared and we want to take the odd part of k squared, then we see here we mix even and odd parts. So this one mixes. So we get a decay controlled by the odd part of R is controlled by gamma plus beta. So we can look at this Riemannian initial data sets. We have gamma plus beta, would be is here, I guess. And then we can see that here the Riemannian, so above this blue line, we have no RT for this Riemannian initial data set. Here we have the weak Regge-Teitelboim conditions for eta equals 1/2 RT for this Riemannian initial data set. And then I guess we do not need this third line because anything below here will have already our Regge-Teitelboim conditions. So we can play around with these parameters and we get almost everything. I mean, the one thing is we can somehow, gamma plus beta will always be better than beta. So we can't get worse things for the scalar curvature than we already see at the K level. Essentially. Yeah, I did over some details, but those are the examples, and this is the behavior in our coordinates. And then I should also mention this beta and gamma being equal to 0 example was already included in this paper by Euclidean and Chris Nertz and has been around for a bit. Part of the prime example. And for this beta equals gamma equals 0 example, you can also find computations for these center of mass integrals. I think both the Regge-Teitelboim one and the CMC one, and see that this oscillates exactly because of this sin ln r term. If one wants to do this for general beta and gamma, I don't think I want to, but I would expect.
Take the sign of R and R
sorry, in
R to gamma. Right. And you take gamma equals 0, take this sign of R instead of a constant.
Yes. I mean, if you take the sine log R here, then you only get an even part and no odd part. I mean, the thing is, so for the Regge-Teitelboim conditions, you get the same behavior. But I think if I remember correctly, if you compute the center of mass integrals for just this sin ln r without the odd part, I think the offending terms canceled, which is very weird because somehow you get, for the oscillations, you get some vector u times some sin ln r thing. So if the u is equal to 0, then the center of mass converges. Still, I think, despite the Regge-Teitelboim conditions not being satisfied, which is also interesting. I think, yeah, probably they have the exact form in the Teitelboim and Nertz paper. And yeah, if I remember correctly, for the center of mass thing, you need this effect of having both an even and an odd part. Also mix otherwise. Okay. Yep. Those are our examples. And now I have 15 more minutes to tell you why these are examples. So. Right. Better coordinates. And actually, the answer to that is thinking about which coordinates might be optimal. And we know from the just asymptotically flat condition, also going back to Bartnik's original work where he showed this coordinate independence of the ADM energy, that harmonic coordinates are very useful and also do kind of give you this optimal decay. So we are trying to do the same here. So the hope would be harmonic coordinates are optimal, and our given coordinates are close enough to harmonic that they are also optimal. And this turns out to almost be the case, and we changed things slightly to have sort of first for this, we have the following theorem proposition, I guess. GKAF with epsilon AF coordinates. Just that we make the decay parameter explicit, 0 less than epsilon. Yes, and also I think I put epsilon less equal 1. That's what happens if you mix it. Of course, already at epsilon equals to 1/2, we get problems because we have separated the 1/2 from the epsilon. Or larger. Okay, such that additionally, we have our odd part of Gij is of order 2r minus 1/2 minus. P, and we are giving this a little index because it's the Regge-Teitelboim decay for G, which is really all that we need for some zero. And then we get several things. So A would be harmonic. Function yi or y1, y3 on all of M, such that y are asymptotic coordinates. And well, unsurprisingly, if we define a V of X as X minus Y of X, then this is O3 1/2 minus epsilon. This is, except for the fact that Bartnik used weighted Sobolev spaces instead of these weighted CK spaces, this is exactly what's in Bartnik. And for the weighted CK spaces, the analysis is also out there in either various papers or now in Dan Lee's book. Very helpful. Okay, and so this is the new thing. The even part of V, let's not put this like this. The even part of this difference is actually better because this sees this eta G. And technically, all of this only works as long as this exponent does not get too small, because as soon as the decay gets too much, we can't expect decay better than 1/r for these things. But we are not in a regime where we need to worry about that anyways. But I could put the maximum of this thing at -1, but generally this will be 1/2 minus epsilon minus eta G. Well, let's put it in. And once we have that, we don't have that much left to do. I'm very slow with writing on these blackboards. So this is A. Then B, purely from the decay of this correction term V, we immediately get that the y coordinates are also asymptotically flat, like Bartnik, but we also get that Hij bar, which is now the G in y coordinates. Then we take the odd component, also in the y coordinates. Coordinates being 0, 1, of R maximum minus 2 minus 1/2 minus epsilon minus eta G. So we see that the Regge-Teitelboim condition on the metric side gets preserved, except for the one curious fact that we here get only up to first derivatives and not up to second derivatives. It's a bit strange. And then the same thing works for the K and the mu and J and R. Mu, I, R. If we now have decay for even O1 or even O0, R minus 3/2 minus epsilon minus eta with eta less equal than eta G plus 1/2 plus equal 1. Then also Hij bar, even bar will be O1 R minus. And I guess I should also give the R's a bar since they are not a Y 3D, but they are equivalent, so that's not the problem. R bar minus 3/2 minus epsilon. And similar for mu. And the curious thing is, and I'm not sure yet if this is a bug or a feature of these harmonic coordinates. The harmonic coordinates, of course, only see the metric and not the K. So any good decay of the metric will give us good decay of the correction term for the harmonic coordinates, which will imply that any bad decay or any good decay on K gets passed on exactly as is to harmonic coordinates. Let's put this even further. If AE not equal to O1, whatever, then also A bar, E bar will not be equal to O1 something, and same for mu. Because really we get lower order correction terms to the K. Which helps us because, now this kind of tells us that if we can find any coordinates where the K's do not decay good enough, then they also will not decay good enough in the associated harmonic coordinates. But if we had any other coordinates where they would decay good enough, then they also would decay good enough in the associated harmonic coordinates, and our harmonic coordinates are essentially unique. So, other than this. the further things, and then this plus uniqueness. Harmonic coordinates. Up to I prime being uy plus a with R3 and this orthogonal 3x3 thing implies that our examples are really examples. I mean, of course, one has to check that this linear change of coordinates does not do anything to the decay conditions, but that is expected. Well, with the caveat that translation and even and odd parts don't work so well with each other, but that we already see here, and is the reason why we, sorry, and this should also be 0, why we lose derivatives. Okay, if you give me, I guess I have 3 more minutes. If you give me 5 more minutes, then I think I can also tell you a little bit about the proof. I mean, the proof is not super difficult, and also it does not involve, it only involves the most simple elliptic PD you can think of, which, yeah, still can get annoying if you're not used to it. But compared to other things, it's really not that hard, and also so, a little bit on the proof. So what is our idea for A? Of course, we want to set up, find Vi such that the Laplace of Vi is the same as the Laplace of Xi, because then the Laplace of Y will be 0. This we can compute from the decay conditions on G to be of O1, and I'm not going -1/2 minus epsilon -1. So then wherever we want to find our elliptic PD theory, or more specifically elliptic PD theory for the Laplacian on asymptotically flat manifolds, tells us that there exist solutions Vi which are O3 1/2 minus epsilon. Now that is the first thing. The second thing would be now about the even part of the V's. We can again set it up as a Laplace problem. We can check what is the Laplace of the even part of V. It turns out, unsurprisingly, because if this were just the Euclidean Laplacian, then the even part would pull out, that this is plus Vi even, which is Laplace Gxi even, and then we can use our Regge-Teitelboim conditions for G to get better decay for this. So this will be O1 minus 1/2 minus epsilon minus eta G minus 1, and this gives us even is O3 minus 1/2 minus epsilon minus. Except now we need to be a bit careful, because if eta is large, then we might end up with better decay than the optimal thing we could expect. So we have the maximum, but I'm not going to write this down. And once we have this for even and odd part, then it just becomes computing changes of coordinates and seeing how this decay of V influences the decay of the change of coordinates, which involves inverting this change of coordinates. And it's a bit annoying, but it has been done plenty of times. Where do I best I think I should delete the first one briefly. So straightforwardly, this implies decay of K bar, P bar, etc., and also decay of K bar even, G bar odd, etc. Note this straightforwardly works as long as we are still taking the even and odd parts in the x coordinates. So we compute our components of the tensors in the y coordinates, then we have functions. These functions give us functions on M. These we put in the x coordinates. In the x coordinates, we take the even or odd parts of these functions, and then we have good decay. And this also gives us decay of these things as good as originally. So here we don't lose anything. We also don't lose derivatives here. But now we have to check what happens if instead of taking even and odd parts still in the x coordinates, we take them in the new coordinates. And then, of course, we have a bit of a problem because essentially our new and old coordinates are related by an additive factor, and an additive factor with reflection does not combine super well. So for lastly, change E bar, and there the problem is sort of the difference between E and E bar is essentially, so the difference is between reflecting first and then translating by this V, or first translating by the V and then reflecting. So this is roughly a K of X plus 2 times the even part of V of X. So at some point X minus K of X. And we also see any odd part of X behaves well under reflection, so that doesn't enter here, but the even part does not behave well under reflections. So this is roughly this, and then a very crude way of estimating this, but if you have anything better, let me know, is to estimate this with the mean value theorem as a derivative of K times or even part of V. And then the derivative of K, as long as the derivatives decay well enough, I'm good, because this gives me like a additional -1. This gives me a +1 compared to the original decay, but it does give me a minus eta G. So the better decay of decay compensates for the worst decay of V even, which it does not need to decay at all. And then I get the additional eta. And also I have 2 epsilons. So this will really be lower order. Yeah, that's essentially what's in there. And if you do it very carefully with all the even and odd parts, you get these very sharp sort of control on exactly where your things go wrong in the analysis. Yeah, then thanks, and sorry for the 5 minutes.